Part 5 of Unit 6 is about polarity and hybrid orbitals. Alright, you've learned about polarity before in terms of polar bonds. In a polar bond, the more electronegative atom has a greater electron density around it, therefore it has a slightly negative charge. Just because a molecule possesses polar bonds does not mean that the molecule as a whole is going to be polar. We have to consider the location of unbonded electron pairs and the other polar bonds to see if they cancel each other out. If a molecule is polar, we say it has a dipole moment. And we illustrate that dipole moment in a Lewis structure by drawing a symbol that looks like this. It's an arrow with a plus sign through it. The plus sign goes on the side with the positive side of the molecule, and it's pointing towards the negative side. So in these examples, they all have polar bonds, but not all the molecules are necessarily polar. In HCl, there's only one polar bond, so you see the dipole moment illustrated in that symbol right here. If you were drawing the Lewis structure, you would just write it above the Lewis structure, but HCl is a polar molecule because there's nothing to balance out that positive and negative charge. If we look at BF3, it's got 3 polar bonds, but the way those bonds are arranged causes that polar force to be canceled out, so it's nonpolar. Same thing with carbon tetrachloride, CCl4. Each bond is a polar bond, but if they're all polar in the same direction, those forces are going to cancel out. It'll be nonpolar. Now, ammonia, NH3, is a polar molecule. It's got the 3 polar bonds, and there's an unshared electron pair on the top of the NH3 molecule that's making it polar. There's nothing to cancel out the force of these 3 polar covalent bonds. Now, CH3Cl, it's going to be polar. It does have something to cancel out the force of these 3 hydrogens, but that bond is so much more polar than the CH bond that it actually causes the top side to stay negative that way. So the only way for the NH3 to be nonpolar is if we had another hydrogen up here. If it was a different element, a polar bond of different strength, it might still be a polar molecule. You guys remember these shapes, right? This is the shape of the sp, d, and f electron orbitals. We need to talk about how they apply to molecular geometry. We think of covalent bonds forming through the sharing of electrons by adjacent atoms. That's nothing new. But in applying the orbital representation of it, we have to think about those bonds forming when those 2 orbitals overlap. So if we look at H2 down here, for the covalent bond to form, these s orbitals have to overlap. For HCl, an s orbital and a p orbital are going to overlap. That overlap area is where the electrons are shared. It's hard to picture the various molecular geometries that we've seen coming from just s orbitals or just p orbitals, just d orbitals or just f orbitals. So what happens is orbitals of bonding atoms combine or hybridize to form new orbitals that allow for more varied molecular geometry. So instead of just being an s orbital or a p orbital, these two can combine with each other to make sp hybrid orbitals. Just like a lion and a tiger, they can have a hybrid offspring called a liger. We can have different molecular orbitals combining to make sp or spd orbitals. And you're probably wondering why this stuff matters. It's abstract, weird stuff, but we really only need to be able to do 2 things with hybrid orbitals. We need to know that they're responsible for the different molecular geometries we have, and we have to be able to determine the hybridization of a molecule. If you can count electron domains on your fingers, you can determine the hybridization of a molecule. The highest amount of hybridization we're going to be dealing with is sp3d2. In sp3d2 hybridization, there are 6 electron domains. So if we had 1 electron domain, we'd start adding to this from the beginning. So 1 electron domain would be S, 2 electron domains would be sp, 3 electron domains would be sp2, 4 electron domains is sp3, 5 electron domains is sp3d, and then 6 electron domains is sp3d2. So let's look at some examples of that real quick. Look at water. There are 4 electron domains here, so we have S, sp, sp2, sp3. We say that water is sp3 hybridized. Let's look at ammonia, NH3. We've got 1, 2, 3, 4 electron domains, so it's S, sp, sp2, sp3 hybridized also. What about something like PCl5, phosphorus pentachloride? There are 5 electron domains, so this is S, sp, sp2, sp3, sp3d hybridized. And we'll look at one more, xenon tetrafluoride, XeF4. This has 6 electron domains around it. So S, sp, sp2, sp3, sp3d, and sp3d2. So xenon tetrafluoride is sp3d2 hybridized. As long as you can count to 6 and remember the order they go in, you can figure out the hybridization of a molecule. Hopefully by this point you know what single, double, and triple bonds are. They're given special names related to how the orbitals of different atoms interact and overlap, and those names are sigma bonds and pi bonds. A sigma bond, which has the symbol that looks like this, I couldn't type that, it's like an O with a little thing coming off the top of it. Sigma bonds describe end-to-end orbital overlap. Sigma bonds are single bonds. Sigma equals single. So all single bonds are sigma bonds. Pi bonds describe side-to-side orbital overlap. So the sides of 2 p orbitals or sp hybrid orbitals are going to overlap. So both of these overlaps are forming one pi bond. Double bonds consist of 1 sigma and 1 pi bond. Triple bonds consist of 1 sigma and 2 pi bonds. Your question for this section: what is the hybridization of phosphorus pentachloride?